Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So it's my pleasure to welcome Tuni, who is a graduate student of Todd Mowry at CMU. He's on the job market, obviously. He's done some really interesting work over the past few years in both the architecture, the programming languages, and the systems community. Really brings a very broad, diverse background, and he's going to be talking about his PhD work today. So, welcome.
Right. Okay. Thanks, Jim. Thanks for the introduction. It's good morning, everyone. Thank you so much for coming for my talk. I'm just going to get straight into the talk. Jim has done a pretty good introduction. So I guess everyone here is probably very well familiar with the challenges that defects in softwares create for computer systems that we use today, in particular when these bugs actually make their way onto the systems of end users. Right? And so this has created a lot of interest in tools that can actually monitor a program while it's executing in order to identify bugs and mitigate their harmful effects. And so one could, in our case, we call this sort of tools Lifeguards. And in particular, what's interesting about Lifeguards is that they're able to actually operate on unmodified binaries. So you can imagine deploying a Lifeguard, for example, to block security attacks, at least until the user is able to patch the software appropriately. And so Lifeguards basically complement a lot of the efforts that developers make to prevent bugs from getting out into the wild. So for this reason, there's been a lot of proposals for Lifeguards for finding different kinds of bugs, ranging from things like data races to memory faults or security vulnerabilities in programs. So a little more about how Lifeguards work. I'm going to use this TaintCheck, which is a security Lifeguard, to sort of illustrate how Lifeguards work in general. So TaintCheck is a Lifeguard that tries to prevent input-based security attacks. So in particular, these are the kind of attacks that would come in perhaps through a network packet, as we have here in this piece of code, and will that attempts to take control of your program. And the way TaintCheck does this, so let me just fill out the rest of this code, of this vulnerable code. The way TaintCheck detects this sort of attacks is basically by tagging input that comes from untrusted source like the network as being tainted or untrusted, and then sort of tracking how tainted data propagates through the program as the program executes, such that when we get to a point where we're about to make a control flow operation based on value that we got from the network, then TaintCheck actually steps in and stops the execution and consequently stops the attack, right? And so what's interesting about Lifeguards, or what's interesting about TaintCheck in this case, is that it actually maintains metadata about the registers and memory locations, which enables it to track how the taint status of data propagates through these locations. To deploy TaintCheck today, or any other Lifeguard for that matter, the standard approach is basically to instrument your binary, your code, your binary. And there are a number of platforms or frameworks available that do dynamic binary instrumentation, such as Valgrind or Pin, and so many others. And basically, essentially, the way that works is, so if we just consider this piece of x86 code here, in particular, this move from a memory location into a register, what would happen is that this instruction will be instrumented with the corresponding TaintCheck rule for propagating the taint status of the memory location into that of the register. And that applies for the other instructions there as well. We will propagate the taint status from the source to the destination in general. And what's great about doing this is that we are actually able to detect bugs early. In particular, bug instructions are identified before they even execute, and they can be squashed. But there's a downside to doing this, which is basically that our program becomes slower. Now, I have sort of shown TaintCheck code in terms of pseudocode, but if we sort of dive in and see exactly what's going on with each one of these rules, it requires a number of instructions basically to propagate taint. So essentially, we are spending a number of instructions to analyze each instruction in the program. So if I inline all of the necessary TaintCheck code here, our code suddenly becomes very slow. It becomes very big and consequently very slow. And so if you then look at the program program at a very high level in terms, and this, let's say we're looking at a program execution where time goes from top to bottom, essentially what we see is that the program, the instrumented program spends it becomes a lot slower, and a big chunk of that time is spent actually running Lifeguard code, right, which makes everything slower. So this leads to the question, well, in terms of how this plays out, here I'm listing some tools, some Lifeguard tools that are out there that have been deployed on binary using instrumentation. And we see slowdowns, average slowdowns ranging from 10x to 30x. So sort of like an order of magnitude is lost, basically, by the fact that we're instrumenting our programs with this very sophisticated analysis, sophisticated Lifeguards. So the fact that we're coupling them together means our program has to run as slow as the Lifeguard itself, which kind of leads to the question, well, what if we could decouple the Lifeguard from the program itself? And this is what I mean by that. If we had the notion that we could run the Lifeguard separately from the program, so what happens then? Well, we improve, of course, we sort of, the Lifeguard itself needs some way to know what to check. So I'm assuming that we can, stream an instruction trace of the program to the Lifeguard for the Lifeguard to perform its checking. And I'm assuming here that we could do this such efficiently, as I'll talk about later. So one immediate impact is the fact that performance improves, right? We live in a world where there are many cores, there are a lot of parallel computing resources available. So having the program and the Lifeguard run on separated resources with little interference just makes them run faster, basically. Right? And in fact, we saw this in the initial research work that I did in this direction called the log-based architecture, or LBA. We saw a scenario where TaintCheck, the average slowdown of TaintCheck dropped from 30x to 3.4x simply by running TaintCheck on a separate core from the program. Another benefit of decoupling is, which is what I spend most of my time working on, is that the Lifeguard actually becomes easier to optimize. So the Lifeguard code can be optimized. And in particular, and I'll talk a lot more about this later, it's much easier or more effective to parallelize the Lifeguard or even apply interesting compiler optimizations on the Lifeguard code. Basically by decoupling it. And I have some results that here where we see that the average slowdown for TaintCheck, so this is on top of the improvements we had before by simply separating them, we could actually get additional improvements. So by parallelizing, we could get the average slowdown of TaintCheck down to about 2x, and by applying some interesting path-based optimizations on the Lifeguard code, we could actually get the slowdown down to about 2.5x. So a final benefit of decoupling the Lifeguard from the program is that it gives us a lot of flexibility in terms of ensuring the integrity of the Lifeguard. In particular, what this means is that we can actually run the Lifeguard in a separate fault domain from the program. Now, when you're monitoring privileged code like device drivers, which can destroy your system in all sorts of interesting ways, this is actually very useful. And this is a big part of my thesis, which I'll talk about later on, in terms of monitoring device drivers and how decoupling helps with that. So I've sort of talked about all the benefits of decoupling. Of course, there are some downsides to it, and probably you've been thinking about that already, which is basically we lose this guarantee of being able to detect bugs early. In fact, we only detect bugs after some delay. So as an example here, I have this piece of code here on the left-hand side, and there's a bug there, and we don't detect that until much later when the Lifeguard is able to analyze the trace that comes from that execution. And so what this means is that containing the side effects of bugs becomes much more difficult. But this is a challenge that I have tackled in my research in terms of monitoring applications and also monitoring in the kernel space. And I'll talk more about that later. So this is sort of the roadmap for the rest of this talk. I'll start out with my early work that I did in terms of how do we take advantage of the fact that Lifeguard has been decoupled to actually make the Lifeguard faster. And I'll talk about two ideas that I worked on. One is parallelizing the Lifeguard, and then doing interesting path-based optimizations on Lifeguard. And after that, then we'll just switch into the kernel space and say, what does decoupling buy us in terms of monitoring device driver execution to mitigate bugs? And there I will describe a framework which I built for my thesis called Guardrail, which actually allows you to sort of protect the I/O state from bugs in the device driver. I'll conclude by basically giving a brief description of what I consider to be my future research directions, and then summarize my contributions. And so, switching to the point to the section where we'll talk about how to optimize Lifeguard code after it's been decoupled, I'll start out by first motivating how do you actually decouple Lifeguards in the application space. And here I'll be describing the log-based architecture project that I worked on much earlier and how that helps to decouple Lifeguards. And then I'll go into the optimization techniques, which is parallelization and path-based optimization. And then I'll come back and talk about some related work that other works that have looked into how do we make Lifeguard code faster. So the basic idea behind log-based architecture, or LBA, is that since we live in a world where we have many cores available, why don't we run the Lifeguard in a separate processor from the program? And if we do this, what we get is improvement in performance, like I showed you before. And so, moreover, since the transistor density is also increasing, then perhaps we could dedicate some more, some more gates into like helping us stream the instruction trace. So we're using hardware to stream the instruction trace from the application to the program. That way we avoid the software costs of instruction tracing. And so we built we built this design, and basically we reserved some amount of memory to sort of cache the log, the trace. And so here, the Lifeguard in this case then ends up becoming like basically a collection of event handlers, because what's happening is we are streaming the application events with the instruction stream to it, and the Lifeguard is just responding and invoking the right analysis code to sort of do the right checking. Now, the containment guarantees that we make in this design is basically that even though it might take us a while to detect a bug, but the guarantee is that the bug will actually not propagate outside the process context of the application. And we're able to achieve this in a couple of ways. One is the Lifeguard itself runs as a separate process, so it's sort of isolated from the application. And two is that we actually stall the program when it gets to when it tries to interact with the kernel. So at system call boundary, we stall it there until the Lifeguard can actually catch up. And we also stall it, of course, when our buffer for which we use for the instruction tracing fills up. And so with this design, we were able to achieve some significant improvements. I have shown the TaintCheck numbers before, but for example, a tool like address check, which basically checks, yes?
Do you do some flow control where you throttle the application because Lifeguard is too slow?
So that shows up basically as the slowdown numbers. Yeah, so the throttling happens because we have a fixed size buffer. And so once that fills up, then it indicates how much faster the program is than the Lifeguard. And so that shows.
How does the signaling happen?
How does the signaling happen? So we do that in the operating system. So we have some operating system support here. Yeah. Okay. So address check is a tool that basically checks for access to unallocated memory. And we saw like an improvement. We reduced the slowdown relative to binary instrumentation from 19x to 3.2x. Lockset looks for data races, and we were able to reduce the slowdown from 30x slowdown to like about 4.3x slowdown. And so memcheck was probably where we had the least improvements, but we still had like close to a 3x improvement in this case. And so this is sort of the baseline for the rest. So this is the baseline for the rest of the portion of this talk, where I'm going to talk about how then do we tackle. So the slowdowns you're seeing here, as the question alluded to, is really the overhead of the Lifeguard computation itself. The fact that we're using multiple instructions to analyze each instruction in the program. And so the question is, how can we make this better? And so the first idea that I pushed was, well, can't we parallelize the Lifeguard, right? And to sort of see why this will make sense, so let's, excuse me, imagine we have an application here and we're just looking at time going from top to bottom, and we're looking at 4 instructions here. In the instrumented case, what ends up happening is we mix up the analysis, we interleave the analysis with the code, and this is really hard to parallelize because it sort of requires the original code to be also parallelizable, otherwise you can't even parallelize here. But decoupling helps us because now if we decouple the analysis of the Lifeguard from the program, then the question is, can the analysis itself be parallelizable? That's the problem we have. And we see that this is possible because the Lifeguard is running behind the application. It means that the application is creating streams of events to be processed. And so there's no reason why we can't just fire off another Lifeguard to process the streams that are further up in future, which the Lifeguard can't get to right now. And this way we can get improvements.
require program support on the actual Lifeguard? So do I have to have language support as someone who writes a Lifeguard, for instance, Valgrind?
Let's see. So the way this works is, yes, we have some minimal API that you need to specify that you're interested. In particular, you need to specify how much parallelism you want. Because that sort of goes to, and it only makes sense if you have as many cores. So yeah, there is some minimal API that you need to change. Yes, sir.
It's not even necessarily easy, even if you have the API. I mean, if you're trying to do taint tracking.
I am going to get to that in a second.
Right.
Yes, as the questioner suggested, there are serial dependencies in what the Lifeguard is doing. So hey, in particular, TaintCheck is a perfect example for this, like I showed before. In order to detect the security attack, TaintCheck needs to track the propagation of data, and this is inherently sequential. In fact, this TaintCheck falls into this class of Lifeguards that do this kind of propagation called dynamic information flow tracking, or DIFT for short. And so memcheck, which detects unsafe uses of uninitialized memory or uninitialized data, also has the same behavior. They are very, very sequential. The computation they do is very sequential. So how do you handle this? And so I came up with this algorithm for parallelizing DIFT, which essentially works as follows. So here, let's say we have this stream of application events that we want to process. What we first do is we break this up into segments and then run that in parallel. In parallel, we run an algorithm called Symbolic inheritance tracking. Now, the basic idea here is that rather than trying to track the propagation concretely, we can symbolically track how taint is inherited. And I'll show that some more details about that later. But it turns out that you can do this in parallel. Right? Now, when you're done with that, then we can then process each of the segments sequentially resolving, because essentially, because of the dependencies, we will still have some unresolved issues, dependencies in there, and we call this, the solving of this, we call it inheritance resolution, which is sort of the next step, where we then sequentially go through each segment and then resolve all of this inheritance. Now, what's interesting about this is that we can actually perform this in parallel in terms of the locations, right? So individual locations, we can resolve their inheritance in parallel. But then for each segment, we have to sort of do that sequentially. And so with this design, we came up with an algorithm that basically has this nice property, although that it has asymptotic linear speedup. Although in practice, the constant factors really prevent our implementation from actually having this behavior. Now, so what do I mean by inheritance, symbolic inheritance tracking? So the idea here is that, so here we're in parallel, we're in the first phase where we're trying to propagate the inheritance here. And so let's start with the very first instruction where we're copying from memory location MX into R1. Well, what is the taint status of MX? Well, we don't know. Well, that's fine. All we just record there is the fact that, well, the taint status of R1 now is whatever the taint status of MX was in the previous segments. Okay? And then we just and so that's the inheritance. So we can then sort of propagate this along as the program executes. And so we end up in this scenario where either we're able to resolve the taint status for sure, or we're able to create an inheritance saying it comes from the previous segment. And so what we've essentially done is we've been able to collapse the propagation chain, which would have been a difficulty for us.
So, can you go back to the previous slide? Sure. So one thing that sort of occurs to me with this is that it looks a lot like carried propagation in the
Yes.
And there are schemes that involve lots of hardware to do carried propagation very fast.
Okay.
Is there an equivalent for this?
I haven't really thought about that, but I mean, is it an equivalent for this? I'm not sure. I think there are some slight differences there because the idea is that we may not really know what the true answer is until we get to the next phase. And so you sort of have to have this sort of, not don't care, but this generic answer, like we don't know what it is. So I don't know if the carrier propagation hardware actually does that.
It does. When you add two bits together, you don't know whether it's 0 or 1.
Or 1,
so
okay.
You have to carry them.
And then in that case, I guess I think it's quite similar.
Yeah.
I think it's quite similar, actually. Yeah, I wasn't aware of that. Yes?
So you'll have to excuse me, I'm a little bit naive on how you do taint tracking, but my assumption is that you do a load, and then if you do operations on that load, to carry taint, you just OR
Yes.
It's an OR across all of the values that you've loaded.
No. I'm sorry,
So
can you
if
rephrase
it
that?
is set as being tainted,
Yes.
then I just OR the results of when I apply operations on that load. Something that's derived from that load, right?
Right,
So
right.
isn't OR an associative operation?
It is an associative operation.
So then isn't this, even though you have a dependence chain, isn't that then a parallel operation by definition? So if I want to add up a bunch of numbers, I can, because addition is associative, I can do this.
Right, but if you don't know, well, okay, I see. So that's assuming you know one of the values, right? Like you know it was tainted. But if you don't know, you can make the wrong conclusion. So it is an associative value, but it still depends on the input values, right? So if it's all untainted, the OR wouldn't change it. But if at least one of the input values is tainted, then the final answer is tainted. At least that's the rule. So maybe I should have clarified that. So if at least one of the values is tainted, then the whole computation is tainted. Right? And that's the challenge.
I think what you said is right for each location.
Yes.
Right, but the problem seems to be that you have the instructions, not the locations.
But if you have the, when,
The
you only
representations.
need to do an OR when that value surfaces. That's, I guess, the point. So there is some parallelism in the fact that you can stall until you actually get, and do what you
okay.
have.
I see. Okay.
And then apply the OR.
It's very fine grained.
Yeah.
Yeah. Right. Yeah. So you sort of have to carry all the values along. Is that what you're suggesting? And that. So yeah, we actually had some sort of a similar problem. The problem is that the amount of computation that you need, the amount of storage that you need to carry that along is huge, and it actually just kills your performance completely. All right, so here we are. So here we've been able to collapse the propagation chain, and we're at the point where we know that the only taint values that we cannot resolve here are the ones that are dependent on the previous segments. Okay, and so then we move into the inheritance resolution stage, and because, like I said, we do that sequentially. So in other words, we first resolve all the segments in J-1. And we have this nice property that then they can be done in parallel, because well, I'll show that in a second. But now we're ready to resolve the taints for the values in segment J. And we can also do that, we can do that in parallel because they all depend on one, they have one sort of predecessor. Your question that you asked sort of alludes to the issue of there might be binary dependencies here as well. We assume that for a particular Lifeguard, it's possible to have like a simplifying operation. So for TaintCheck, for example, when you combine let me see how I can rephrase this. For memcheck, for example, if you have at least one initialized value, it doesn't matter what the other value is. And so for TaintCheck as well, if you have one taint value, it doesn't matter whether the other value is untainted. So you can actually always collapse it easily. And so that's, we get this nice property that we don't need to worry about binary operations. And so once we resolve this, then we can go ahead and then resolve the inheritance for the next segment. And so in terms of the implementation, I basically built the parallel TaintCheck in this way, where I have a bunch of parallel workers, but I have my inheritance resolution is done sequentially. So I have a single thread doing the inheritance resolution. And so we sort of call them the parallel workers, and then we have a master, essentially. And a way to sort of compare this to sequential TaintCheck is that you assume that you have the master is equivalent to one sequential TaintCheck, and then you give it a bunch of parallel workers to sort of help it improve performance. And so what does this look like in terms of performance? These are some spec benchmarks. And here I am showing the speed up over LBA, so over a sequential TaintCheck running on LBA. And we saw some pretty decent improvements, and this is with 8 workers. So the speed up is not quite linear, but we did see some interesting improvements. And we saw, in some cases, up to 3.4x. On average, we saw about a 1.7 improvement over the sequential approach using 8 workers. And this sort of shows that there is opportunities to improve performance by parallelizing. We might even get some more if I had parallelized the master, for example. But we did, yes?
So what's the slowdown of TaintCheck with LBA?
With LBA, it's about 1.9x. So yeah. show that a bit earlier. Okay, so yes.
Picture show that one processor is both a worker and a master.
In question.
The leftmost.
Oh, so you mean this leftmost one? Oh, sorry, that's not what's going on here. So these are the workers, like the symbols indicates the workers. And the only thing I'm doing here is the fact that, so there are 4 segments, and then the master, which is the symbol, works on each of the 4 segments. So maybe this figure is confusing. It's not really like the same processor. I mean, it could be, but it doesn't have to be.
Do you know, is the master the bottleneck here?
No, it's not, actually. It actually turns out not to be. The bottleneck here really is that this inheritance tracking doesn't shrink, the segments that come out of it are still quite big. And so we could either try to like break down segments even more, but it turns out not to help so much, right?
How big is big?
Big is like half of what he gave us, so it only shrinks it by half. So like this, I give it a segment and it only shrinks it by half. And then the other thing,
The number of uprightly exposed
Right.
values is half of what's in the...
yes, we're only able to eliminate half of that, yeah.
So how big is the segment though in terms of instructions?
I think for this, it was, I played around with it. I think this was probably like 16K. This results were for 16K. Yeah, 16,000 instructions. Probably the other interesting thing, which I sort of left out, is that the inheritance resolution is about twice as slow as just propagation. So so that's these guys are, half the speed of the sequential TaintCheck. So that's the cost you get for symbolically tracking inheritance rather than actually tracking propagation. Any more questions? Okay. All right. And so, what if you don't have many cores to commit to making your Lifeguard faster? What else can you do? Well, one approach is, why don't you do path-based optimizations? And you might ask, why path-based optimizations for Lifeguards? Well, because the compiler community has shown for so many years that most programs, the execution time is dominated by a few hot paths. Now, so if we consider what happens when we instrument those hot paths, we see a number of results. And so here I have instrumentation of the hot paths. The colored bars are the analysis code. I've only used different colors in this case to maybe hopefully delineates the different instrumentations, while the black lines are basically the original code. And so we have something like this, like one of these basic blocks will open up to something like this, where we still have a lot of analysis code in there. Well, so if we consider one such hot path that's been instrumented, we can conclude a number of things. One is that the Lifeguard code is actually spent most of its time analyzing the hot paths, right? So the overhead of the Lifeguard itself mostly comes from the hot paths. It also means that if we could somehow optimize how the Lifeguard, analyzes this hot paths, which run frequently, then we could improve performance overall. But the challenge to doing this with instrumentation is that this requires you to analyze across 2 different kinds of code, right? There's a program code and there's the analysis code, and there's some context switching code in between them. This is just really, really complicated, right, to find redundancies here. And this is where decoupling helps us, right? So by decoupling the analysis from the Lifeguard from the program, we can just focus on the Lifeguard code itself and see if we can improve it by analyzing along paths. And so here I have basically the Lifeguard code that is the correct analysis code for this particular program path. And we call that sort of unoptimized, because we sort of just pull them out and sort of execute them in order, and so it's unoptimized. Now, even with a standard compiler, you could imagine that if you inlined all of this code together, a standard compiler could probably find opportunities to, constant propagate or maybe save and restores here. So we could get some improvements there. But the real big win comes from the fact that, the Lifeguards have a particular way they compute, right? So TaintCheck propagates. And so if we could exploit the domain knowledge of this Lifeguards, we could actually get even bigger optimizations. And one example, which I'll talk about today, is how the Lifeguards access their metadata. So the metadata is basically what, the taints values, how they access it. And also, you could also eliminate things like the redundant checks. You can find redundant checks because you know that's what the Lifeguard is doing. And as an example, so here is the path handler for a particular MCF, for a particular benchmark from spec MCF. We start out with like a path handler, that's the taint analysis path handler, that had 86 x86 instructions, right? Now, when we sort of compose the path handler together and give it to a standard compiler to do inlining and constant propagation, we're able to like eliminate 5% of the instructions. But when we apply TaintCheck specific optimizations, we're actually able to blow away about 45% of the instructions, which is like a big win. So I talked about how metadata access is like a big source of overhead in Lifeguard. So let's consider TaintCheck, for example. And I'd shown this before where, to propagate the taint of a memory location into that of a register requires like 7 x86 instructions. But what's interesting is that 6 of these instructions are all to derive the metadata. And the reason for this is because most Lifeguards use 2-level tables to shadow the whole memory, right? This is like probably the most flexible way of doing this, right? So you have 6 instructions that you have to execute each time to obtain the metadata. So the question is, what can we do to improve this? Just looking at the Lifeguard code itself, I mean, I've represented the memory locations with A, B, C, and D. It's very hard to say whether there's any similarities in this because remember, all of this is just coming and streaming. This values are just streaming in from the log to the analysis, and it's hard for us to tell, is there any real value here? I mean, are they similar? Is there optimization opportunities here? But instead, what if we looked at the application path itself? And if we do that, we see something very interesting. So I've circled all the corresponding memory accesses in the path, in the MCF program. And what we can see here, well, is like the first 3 are exactly the same address because, the register doesn't change, so it's exactly the same address. So, A, B, and C are actually A, right? And then what's also interesting that even though the last one is not the same address, it's actually close enough. It's like 64 bytes away from A, which basically means there's a higher probability that it falls into the same second-level table. So we could actually, the page table, we could leverage some of the work that we've done for accessing A. We could use it to also access B, the other location D, much faster. Now, what was interesting, at least cool to me when I did this was like, wow, I wanted to optimize my Lifeguard, but I couldn't find anything in my Lifeguard code that to help me. I had to go and look into another program, which is basically the application that I'm monitoring. And there I was able to find useful information that was able to enable me to implement this optimization. And so like an interesting, for me, it was really cool, being able to like optimize a program by looking at another program. And so this is basically where the results that we had, that I got for this. And so here I'm showing average speedup over LBA on the y-axis in percentages. And I'm showing 2 results. One is if you give a path handler that you've composed to a standard compiler and it could perform inlining and constant propagation, what kind of improvements would you get? And then when you implement a Lifeguard specific optimizations like the kind of described. And here we see that, well, the standard compiler does pretty well in some cases. Like GCC, you could get a 21% improvement over standard LBA, but in some cases it's bad, and it's like Locke said, the problem here is the fact that when we inline all these handlers, we basically increase the code size, and that hurts, right? But the cool thing is that with Lifeguard-specific optimizations, we always do better, and sometimes even quite significantly, like we have a 61% improvement here for address check. And so by leveraging domain knowledge of what the Lifeguard is actually doing, you can actually improve the Lifeguard code significantly than simply using standard compiler tricks.
Suppose I ran a profiler that tried to figure out hot basic blocks and hot functions, and then applied that, basically inlining and reorganization of basic blocks based on that profile information. Do you think GCC would then have been able to pick up a lot of the optimization opportunities that Lifeguards?
That's exactly what I did, actually.
Okay. So
that's exactly, yeah. So I figured out the hot paths, and I presented it both to a GCC and then to my new compiler, and this is sort of the results. Yeah. Okay. All right. So we get improvements this way. All right, and so in terms of our related work into how do we make Lifeguard code faster, we could sort of categorize them based on whether they were targeted for coupled lifeguards or decoupled lifeguards. So for the coupled lifeguards, there were, so Chin basically accelerates TaintCheck based on the observation that most locations have a stable taint value. So they're either always tainted or always untainted. They never really fluctuate. And so I was able to use that to do less taint propagation. Dalton basically proposed doing TaintCheck in propagation in hardware, and that helps. And then more recently, Bozeman, they've come up with some interesting techniques of using on machines that have, like Itanium, that have machines that have many registers, basically partitioning your registers for taint checking and for your actual program. And they got some improvements there. And then they had some interesting but custom metadata organization that probably only works for TaintCheck. And in the coupled space, well, a bunch of this work two of this work is the ISCA work. We had some hardware accelerators. And then this is hardware acceleration is both the ISCA and the Vlacos work. The Nightingale work actually was kind of interesting. So they parallelized the TaintCheck as well, and basically they found some good speed ups. But one of the results that they had from there, which I didn't talk about today, is the fact that you need at least 4 parallel workers before you can actually match the speed of the sequential, simply because of the custom factors. And Corliss is basically a hardware extension in the commit phase where the analysis is performed at commit time using special hardware. So at this point, we're going to sort of switch gears and sort of dive into the next part of of my talk, which is where I'll talk about using lifeguards in the kernel space, basically the Guardrail work. So the outline for this is, first I'm going to motivate why did we consider device drivers as target application for lifeguards in the kernel space, and then I'll give an overview of Guardrail and what sort of the design goals that we had in mind. I'll sort of look at some related work in that space. Then I'll talk about how do we do containment, right? So we're going to be detecting bugs after the fact. So how do we do containment? And then I'll present I wrote 3 new driver lifeguards. I'm going to present their bug detection effectiveness and their end-to-end performance. So why drivers? I guess probably the wrong community to be asking this question. Well, it turns out they're an important part of our software stack today, right? They allow us to use our hardware devices that we love, but unfortunately, they're a major source of bugs. And so one particular operating system reported that 85% of their crashes were due to drivers. And then the other thing that's actually interesting about them in terms of runtime monitoring is the fact that drivers are actually very sensitive to perturbations, which is something that you don't see in the application space. So this is because a lot of their computation is timing sensitive. So responding to interrupts is timing sensitive. If you stall it significantly enough, you actually break the driver. And so for this reason, this has been the key limitation to applying sophisticated analysis to drivers, right? Because you slow them down enough, you just introduce a new set of reliability issues, right? Besides the one you're looking for. So what does Guardrail do? So Guardrail is a system that I built for using decoupled analysis to actually mitigate driver bugs. In particular, I'm looking to protect the I/O states, the persistent I/O state from driver bugs. And the way Guardrail works is basically it streams an instruction trace to the lifeguard, and then it interposes on the interface between the driver and the device, such that I/O operations are not allowed to pass through this until they've been verified by the lifeguard. And so there, the lifeguard can run any arbitrarily sophisticated analysis that you can think of. And so with this, we had a number of design goals, which Guardrail meets. So the first is we wanted containment, right? So we wanted to protect the external world, starting from the device, from bugs in the driver. We have the unfortunate effect that the operating system kernel is still sort of vulnerable to driver bugs. And we're able.
Is that because the Lifeguard runs after the instruction has already clobbered your kernel?
Yes, because we don't have an interposition layer there. Yeah.
Are you going to tell us how you implement the interposition layer on the other side? Because I'm not sure how you did that one either.
Oh, you mean on the kernel side?
No, on the between the driver and the
Sure.
device. Okay.
Yeah. And also, but the fact that we run the Lifeguard in a separate protection domain, which I talked about earlier, means that even if the driver hoses the system, our Lifeguard is still able to at least tell us what went wrong. But in reality here, if the driver hoses the kernel, the Lifeguard can still tell us exactly what went wrong.
Do you also handle things like DMA?
Yes, in an interesting way, I'll get to that too in a second. Right. So the other sort of design goal we had was generality. So drivers suffer from a variety of bugs, buffer overflows, data races, all sorts that you can think of, security vulnerabilities. And so we wanted a system that allowed Lifeguard writers to write arbitrary analysis. And we sort of hit that by making the Lifeguard sort of be a separate component that you can just implement your new analysis in it. And so in particular, and also our interposition layer is actually transparent. It doesn't require changes to either the driver or the device. And so it allows for generality. It allows us to support arbitrary combinations of drivers and devices. And in particular, in this work, I looked at about 11 Linux drivers from 4 different classes, so audio, storage, network, and disk. And also I implemented 3 new Lifeguards for finding concurrency, operating system protocol errors, such as DMA, and then memory safety. Yes?
Specify prevention of corruption of OS state itself.
Sorry, I didn't.
So do you prevent corruption of other OS state or just the corruption of the device?
Of the device, yeah. So here we're just safeguarding the IO state from the driver bugs. Yeah. So yeah, the kernel is vulnerable to bugs in the driver, and it's in Guardrail.
Do you actually run the Lifeguard completely offline?
This is online. This is all online.
How much buffering do you have to do for this instruction tree? Because that can explode very fast, right?
It doesn't matter. It really doesn't explode so far because when you think about the instance of time when drivers execute, it's only brief periods within your overall execution time. And so the driver is not, unlike applications which are it could be CPU intensive and run all the time, drivers only run intermittently and they might run for a burst, but then they go off and do some IO and they don't run for a while, right? Yeah. Okay, questions? So detection fidelity is essentially that some bugs just require instruction level analysis. And so we want to support that, and we do that by basically providing the Lifeguard with an instruction trace. And finally, trustworthiness. And the idea here is that, well, ultimately we have to make some changes to the trusted computing base, and we wanted that to be minimal. And in particular, the IO interposition is the only layer that we need that really needs to be in the trusted computing base. And by ensuring that the only thing that it does is basically intercept the interaction between the driver and the device, it doesn't really do any sort of computation to detect errors. That's actually decoupled off to the Lifeguard. So that way we can, it's at least conceptually, it's very simple. And so that helps for the trustworthiness of a TCB. Now, in terms of existing work in this direction, in terms of driver reliability, there's been a lot of work. I think we can categorize existing dynamic approaches along 2 different axes. So the first axis, which are the columns here, is exactly when does the dynamic approach perform its correctness check-in, right? So you have the coupled approach, which is you perform the check-in before every driver instruction, or the decoupled, which is sort of like my work Guardrail style, where you do the check-in at some time later. And on the other dimension is how much of the driver execution is checked by the dynamic analysis. So you could either check all of the driver instructions, or there are a lot of techniques that check only the API interaction between the driver and either the kernel or the device. Now, these design points matter because they impact things like performance, right? So one way to improve performance is basically to check just the API calls, right? You ignore the bulk of the driver execution, right? Another way to improve to get good performance is to decouple it, so run the checks, sort of asynchronously. But of course, this all comes at a price, right? So if you check only the API, the driver API, then you have poor fidelity in the sense that you miss a lot of bugs that occur within the driver itself. And of course, if you decouple, then you have this containment challenge, which I'll get to a little later. And of course, the other properties sort of fall in place. And so in terms of our existing approaches mapped in, we have this sort of picture. And so perhaps the most immediate one to observe is that there's only one prior work that does like decoupled checking, and that's AfterSight. And AfterSight provides like no containment at all. So it's only good for it doesn't protect anything, let's just put it that way, because it detects the errors after the fact. It has no containment. And so in terms of the coupled approaches, which is the majority of the approaches, we see that there's a lot of work in checking only the API to improve performance, right? So it's where people sort of optimize for, so they want good performance, and so they only check the API. And so of course, the problem with that is that you miss some actual bugs. So Guardrail sort of sits here in the decoupled and checking all the driver instruction space, right? And the downside there is the containment, and I'll describe how I address that, how I solve that.
Can you say what you mean when you put like software fault isolation in the upper half of this? I mean, I usually think of that as checking all instructions that run.
Right. So software isolation is basically almost like sandboxing. So the idea is you're fine with the module that you check in corrupting its own internal data structure, but you're just saying it will not get out. But the problem there is that, well, while you could prevent things like writes that would directly corrupt the external world, but there's a question of whether your module itself is behaving correctly at a fundamental level. I mean, if it's constantly overflowing its own buffers or corrupting its data, is it even doing the right thing? It might not be able to corrupt the kernel, but is it even providing the functionality that you want?
So you're worried that it's going to corrupt the device because inside the driver, the wrong things are happening? Yeah,
exactly, and it's a good point, right? So even like a lot of the fault isolation is really been about the interface between the driver and the kernel. Really, the interface between the driver and the device is something that that doesn't actually fall into that as well. But even just is my driver behaving correctly, right? Even if it's not crashing, is it displaying the right images, right? It may display the wrong images without actually crashing the kernel, but then that's not what you want. Right.
I guess the follow-up question is, how many of those crashes that you mentioned are actually because of things? I mean, drivers doing bad things to the device as opposed to they doing bad things to the rest of the OS.
Well, how many of which crashes? Well, I mean, I didn't mention any particular crashes, but I can answer your question. And the answer there is that yes, the challenge is that let me put it this way. So crashes that come from the driver corrupting the kernel are well studied, and there are a lot of numbers there. Unfortunately, crashes that come from the driver corrupting the device, there are not that many numbers on them. But there have been some really interesting cases. So, for example, a few years ago, there was this E1000 network card that was basically being hosed by a driver, right? And your network card literally just dies. And the other challenge there is if your driver actually hoses your disk, for example, it could cause some other kind of failures that's just impossible to trace. So it's really hard to actually quantify how bad this is. So, I mean, imagine that the driver actually corrupted your virtual, so you have virtual memory, right? So you're storing stuff on disk, and you think your virtual memory is working well. What if the driver just scribbled over all of your virtual memory metadata, right? Your operating system starts failing in all sort of arbitrary ways, and it's very hard to sort of quantify this. I think this is part of the challenge why there hasn't been a really good study in terms of this kind of failures, because they tend to be very catastrophic anyway. Yeah. Good questions. Okay. But then, so the other dimension to look at dynamic approaches is what system components are they protecting? And like I said, well, most of the work has really been in terms of protecting the operating system kernel. It's only recently that people started looking at protecting the I/O device state, and so Guardrail sort of falls into that space, right? So we thought that was like an interesting area to go after. The other space is really well congested. There's been a lot of good work and interesting results from that direction. So I decided to just pursue this new space that is fairly new.
Can you talk a little bit about Nexus RVM?
Oh, sure.
It protects both, right?
Yeah, it protects both, yes, yes. So, so Nexus RVM protects the kernel by basically running the drivers in user space. Okay, so that has memory protection. And then it protects the device by basically, it requires you to it requires the hardware to basically write a reference validator, which indicates how the driver should interact with the device. And so by trapping all this, so now that the driver is in user space, you can essentially trap all of its, well, you basically change its API such that all of its interaction with the device actually turns into system calls. And so you can interpose on that and then check that against the model, right? Which sits, and the reference monitor sits in the kernel and then verifies basically that the driver is, interacting with the device in the right way.
The reference monitor has to be written manually.
Yeah, it has to be written manually. It's very hard. It's specific to that particular device, and it's not clear that it could be written in an open source fashion, because for devices that are proprietary, it reveals probably way too much about the smarts that go into the device itself, right? So, sorry?
So performance.
Yeah. So yeah, but it was really the first work to really look into dynamic land. And they also made this interesting observation in that work where they said, like, we banged on our device hard enough without RVM, and then our device stopped functioning, right? So they sent like all sorts of random data like inputs to the device, and they actually killed the network card as well as part of the research. It's kind of cool. But Guardrail sort of falls into this space. All right, so containment, which I guess seems like has a bunch of interests here. So how do we contain bugs if we detect them after the fact? How do we prevent it from corrupting the device? So, so let me just rephrase the bug containment challenge. Here is we have a driver code. It's running. It's had a bug. It's gone past the bug. So time is going from top to bottom. The analysis is still somewhere back, still checking some of its history, and the driver is going to do a disk write at some point, right? And so the question is, okay, is that bug going to going to cause terrible things when this disk write happens? What can we do to prevent this from happening? And so, in other words, we have this challenge that we need to preserve I/O integrity, even though we're detecting bugs after the fact. And so I looked at it and said, well, this is because the driver talks directly to the device. So why don't we just put something in between them? And virtualization seemed like a really good approach to go. So I built something around a virtual machine monitor where I added an interposition layer here. And so with Guardrail, so this is how I/O operations get executed. So first, we intercept the driver issues an operation and we intercept it, okay, in the interposition layer. And then we send a request to the Lifeguard, which is analyzing and say like, oh, is it okay to let this access go through? If you like caught up, eventually, let's say in the good case, it says, yeah, it's okay, you can go ahead and do it. And then the interposition layer then replays the access. I don't know, should I take your question? Okay, very good. It replays the access. Now, what's cool about this is that this is transparent to the driver and the device, right? So the driver doesn't know that this interception occurs, and the device doesn't know that the access is coming from the virtualization layer, not the device, right? Not from the driver, right? And in particular, we do the interception using traps, and we complete the operation using emulation, which provides some performance challenges.
So pre-playing Anirudh's question, how does
Yeah.
this work with DMA?
Wait, what?
DMA.
So there are two parts to DMA, right? There's the control part, and then there's the actual streaming data part. So what we are trapping here is ensuring that the control part is correct.
So the control part could just be a data structure, like a network transmit queue that's sitting in memory, and the driver is just doing memory writes to enqueue packet transmissions by enqueuing stuff in a memory data structure. And asynchronously with that, the device is walking this thing in memory and pulling packets out of it. So the control channel, to the extent that it exists, the control channel is just, I wrote some stuff to memory.
No, it's a little more than that, because the driver has to tell the device where it wrote stuff into. The driver is not just going to, the device is not going to just go to some arbitrary location and start reading from there.
No. So the driver might tell the device, here's my transmit queue.
Right.
And the device starts transmitting.
Right.
And as long as there are still packets in that queue, the device will keep transmitting. The network device will keep transmitting.
Right.
And the driver can happily enqueue more stuff there. And it doesn't have to tell the device, I've got another packet, I've got another packet, I've got another packet.
Right. Right. So
there's this asynchrony.
So right. So eventually, right. So even with this asynchrony, right, at some point, right, the driver has to be done and has to tell the device that it's okay to get the data. At some point, right. Or either the device has to generate an interrupt to indicate that I have completed. I mean, it's a transaction at the end of the day, right? So.
Well, maybe we should talk about
that
later.
Okay. All right, continue.
My argument is that there's a control channel, but it's asynchronous in the sense that the driver can get stuff done without having to invoke that for every operation. And I'm sure that in this system I could slip things out to the device without.
Oh no. Okay, so now I think now I get your question. Right. So the driver could write corrupted data and slip it out, but it would not modify the state of the device itself. Right? Because the control data that you send in, the I/O data that your packet queues are not actually going to affect the state of the device itself. You can only do that by programming these device registers and sending them in some arbitrary values.
Let's talk about it later.
Okay. All right. So, but by doing this, I mean, there's a performance implication for trapping and emulation. But by doing this, the design trade-off that I made was that I would rather like stall I/O, the device register reads and writes, which are the I/O operations, which are typically slow anyway, and they're relatively infrequent, rather than impacts the actual CPU instructions of the driver, which are much faster. But of course, there's some performance overhead implied here. And we can see that here. So here I'm showing performance relative to Linux, so where Linux will be 1, and so lower is worse. And here I am evaluating the performance of using Zen. So I built this in Zen. I added this interposition layer into Zen. And so I'm comparing against Zen, and there's the I interposition numbers. And I did this for basically 4 classes of devices, so audio, video, disk, and network. And the idea is to say, what is the performance impacts of doing this sort of interposition on every device register read and write, so every I/O operation. And what we see is that in most cases, the overheads are not so much. It's like about 10%, and this is because these operations are slow anyway to begin with. And then they're they're infrequent, right? But there are cases too where it gets worse, right? So one of the cases where I have a very poor number is on compilation, right? So where we're losing about 30% of performance relative to Linux. And it turns out that, well, the virtualization, Zen is not doing much better. So, it seems like most of that overhead is coming from virtualization, right? But with Memcached, where I have the system fully saturated, I'm losing close to 40%, about 40% of the performance. And so here it shows both sides of it. So like 20% of that seems to be coming from virtualization, and the other is coming from the fact that, so I'll show a little bit later, Memcached actually, for this particular workload, actually makes the driver do a lot more I/O operations. The amount of data, the get size is about 64 bytes. So it's doing more I/O operations per byte. And so in those cases, we can see the slowdowns. But that, in a nutshell, is sort of how the interposition works. So now what does this allow me to do, right? Even though I have that, now I can write some new interesting tools that have not existed before. And in particular, I wrote these 3 tools. drcheck finds data races in drivers. DMA-check finds DMA protocol bugs, while DMcheck finds memory bugs, uninitialized use of unsafe use of uninitialized data, sort of like memcheck in the user level. In the interest of time, I'm going to focus only on this first 2.
So one thing Nexus was that the reference monitors, they had to write them for each device that had to know about the device. Are the things you're talking about, is the I/O interposition and these checkers, are those per device or are those general?
So the I/O interposition itself is general, and the reason for that is because it only intercepts the memory. It intercepts the operation in sort of like a device agnostic way. So it's essentially a trap, right? So the driver will map the device's memory into its address space and try to touch it. And I mean, the detail is like, then I just revoke that so that every access to it becomes a trap. And so this works regardless of the driver or the device.
So you just need to know where the control registers are mapped into memory.
Yes, exactly, right, exactly. And I mean, there are like standard APIs for how to do this in the kernel. And so, so yeah, at least within a particular operating system kernel, it's general in that sense.
But to go back to your motivation of,
Sure.
of drivers that have bugs that cause hardware to be corrupted,
Yes.
like the network card thing.
Yes.
To catch that, you would need to write a checker that understood the device's interface.
So I will put that in a class. So there, like I said, there are a wide variety of bugs that drivers could have. So it's conceivable that if I gave you an instruction stream, you could actually write a checker, instruction trays of the driver. You could actually write a checker and again, to check for what the driver is doing and how it's programming the device registers and find such bugs. I didn't look into that in particular for my thesis because one of the challenges of doing that is you sort of need to know how the device behaves, right? And that seemed like really hard. So this is sort of like the easiest things I could do using like open source information. Like, right. But I believe very much that you could actually write similar checks. All right. So I'm going to start with DRCheck, which finds data races. And so it's a quick primer on background on data races. So a data race essentially is two accesses to shared data, typically from two different threads, where at least one of the accesses is a write, and they're not serialized. And so, like example we have here will be a data race, right? And like a lot of the work in data race detection has been done in the user space. And so some of the techniques they've used are things like trying to infer whether there's a consistent lock-in discipline for protecting shared data. So this would be the lock-set approach, where we can see here that this access here with this locks here, that this access here is safe because the X is consistently protected with lock LX, right? And then the other approaches they use happens before, which is based on the fact that, well, you know, certain operations are serialized in time, so like a lock and an unlock on the same lock are sort of serialized, and so you know, one happens after the other. And so the techniques that do this, and so here, and then in addition, they maintain a vector clock to sort of keep track of what time was. And so here we'll see that we can conclude that, you know, this access to X here is safe. So this is the vector clock of the variable, and it indicates that thread 1 wrote access this variable in its epoch time of 2. And this is the vector clock for thread 2, and relative to its epoch time of 3 for thread 1. And so the access is serialized in time. And then there are hybrid approaches that combines, because both approaches have different complementing strengths and weaknesses. And so it sort of, I think, sort of covers there is detection at user level. So you might ask, well, why not just use these tools in the kernel, right? What's interesting? Well, it turns out that kernel mode, concurrency in kernel mode is vastly more complicated than the user level. And so one of the things that could happen is that things that are actually racy in the kernel space will appear as being safe to a user level detector. And one example is this notion of inter-thread concurrency. This is when a thread actually races with itself. Right, so when I was defining data races, the common definition would imply that there has to be two threads involved in creating a data race. In the kernel, this is not true at all.
What does that mean?
I will get into that in a minute. So I'll go into that in a minute. And then the other problem is that safe accesses, so well-serialized accesses in the kernel, will actually appear racy. And this is because in the kernel, synchronization is done using other things besides mutual exclusion primitives. In particular, there's a form of synchronization called state-based synchronization, where drivers serialize their operations based on the state of the device. And I'll talk about that too. So there's only one work that I'm aware of that found data races in the kernel mode dynamic approach, and this is called Data Collider. And the way it works is basically, so say here we have this access, we have the shared variable and two threads. Data Collider will stall a thread at a shared memory access, and then set a breakpoint on that data. And the idea is that if some other thread comes along and tries to access it, then there'll be a collision because it obviously means that thread was not serialized relative to this to the stalled thread. And so the cool thing about Data Collider is that it has no false positives simply because it doesn't need to worry about the synchronization primitives or protocol and things like that. It doesn't worry about it, and it only actually reports actual races that actually occurred. So that's a strong. But then the downsides are basically that, well, because it stalls threads, it cannot stall threads that are timing critical, like interrupt handling threads. So if the first access is from an interrupt handling thread, then Data Collider will not stall it and will miss the race. And also, it cannot stall threads indefinitely. It has to let them go eventually. Now, this is less of a problem because typically maybe no data corruption happens if the two conflicting accesses happen far apart in time, but it's still a near miss, and we would like to know that the two conflicting accesses occurred far apart in time. We would like to know that. So let me get back to sort of the things that might appear that are racy in the kernel might appear safe to user space. So this is inter-thread concurrency. Now, what is this all about? Well, the idea is here that the kernel typically has to perform a wide different types of tasks of different priority levels. And so a kernel thread actually doesn't execute in just one context. In fact, if we looked in the Linux kernel, threads could either be in a process context, which is dubiously named, which it really means that it's actually servicing a system call from the user level. Another context that the same kernel thread could be in is in a top half context, where it's a servicing interrupts that are generated by the device. And then in the middle, we have this bottom half. And the idea is that the top half is the highest priority context. And so if a kernel thread is doing system call stuff, and a packet arrives on a network card, we're going to interrupt it and use that same thread to go service that interrupt, right? And this is and just to show as an example, we have here a network driver. It starts out in time 1. It starts out in a process context, sending packets, the send system call, and packets arrive. And so we need to move it into the top half. Now the question is, what happens if it accesses the same data in both contexts, right? This is actually a race, even though to a user level detector, it's the same thread, so it's serialized. But no, this is actually a race. Because eventually when it returns to the process context, the context is not aware that another change has happened, right? And so the driver can get into an inconsistent state. Now, Data Collider can detect this kind of this particular example here because it can stall the thread while it's in process context, and then when the thread tries to access it in the top half, it will actually detect that because it will fire off the breakpoint. And so, the basic insight from here is essentially when we think about concurrency race detection in the kernel, we need to think not only about the threads but actually the context in which they're executing. Now, in terms of state-based synchronization, so this is where something is well serialized by the driver, but it might appear to be buggy to user-level detector. Now, the basic idea here is that, well, the devices are themselves like basically finite state machines. You can view them as finite state machines. They go, and here I have sort of like a snippet of a network card where it starts out in an inactive state, and at some point it gets connected to the PCI bus, and at some point it gets initialized and it's ready to do packet transmission. So if I consider this network driver code where, well, the same flag is being updated by two different functions, which could be executed by different threads, but they don't seem to be serialized, then my ask, is this a race? Well, it turns out not to be a race, simply because the probe function here is only valid when the device is in an inactive state. It's actually what takes the device from an inactive state into, connects it to the PCI bus. While the open function only gets called after the device is already connected to the PCI bus. So in reality, these two functions are serialized in time. They'll never execute concurrently. And so this is actually not a race, but a user-level detector, because it doesn't see any explicit concurrency between them, will think that this is a race.
But Data Collider will report this as a race.
Data Collider will not. Data Collider has 0 false positives. I had that on the slide. Right? It has 0 false positives, so it's a great thing about it. But this is a problem, actually. So this actually goes to a fundamental problem, which is that by being agnostic to synchronization protocols, Data Collider will not have this sort of problem regardless of whatever new fancy synchronization protocol comes up in future, right? That's really cool about it. But Guardrail, we're doing trying to understand synchronization protocol. So we're sort of susceptible to this. And in particular, because devices have different kinds of, the states in devices can vary.
Why are you doing that? Why don't you just use data collider's trick?
Why don't I use data collider as this? Well,
the trick, right? I mean, this trick of just
so combining,
doing
yeah.
that write read thing, right?
Actually, it's an interesting direction. So we're balancing the strengths of data collider, actually, in fact, using it to help eliminate the potential, the dependence that DRCheck has for synchronization protocols is actually an interesting direction of research, right? But here I wanted to just really push as far as I can in terms of if I try to understand the synchronization protocols, what would that look like? Right? And so the challenge that comes from this is that devices are very different, right? And they have different states. And so how can I possibly encode all the synchronized, the different states into my tool, or even for a device that hasn't been invented yet? So at this point, I had to make a trade-off, right? I can't possibly track all the possible states that a device could have, but fortunately, the kernel itself is also aware of some of the states, because the kernel is actually what invokes the driver code, right? And so, for example, here's the networking stack code that invokes the open function of a driver. And you can see here that it's actually checking to see that the device is actually connected to the PCI bus before it's doing that. And so in DRCheck, we basically leverage this fact that some of the states are already exposed to the kernel in a standard way. And so we essentially just track those kind of kernel visible states. So whether a device is connected to the PCI, whether it's generating interrupts and things like that. So this allows us to sort of handle a wide variety of drivers, but it also creates a potential that we may miss synchronization. We may have some false positives, and I'll have those numbers in a second. So in particular, what are the false positives that we have? So for my comparison, I started out with Data Collider, which has 0 false positives. This is all, okay, let me just rephrase this. Well, Data Collider has 0 false positives. So this experiment was done using Linux drivers. Of course, Data Collider is only available in Windows, as far at least as when I was doing this evaluation. But it has 0 false positives, so no big deal here. Now, kernel lockset is a tool that I wrote where I took a user-level lockset, and I basically made it aware of the locking primitives that exist in the kernel. And then I applied it, and then, whoa, I get all these false positives. Simply because there's this synchronization protocol in the kernel is different from that in the user space. So when I applied but in DRCheck, we do better. I mean, we still have some false positives, and a lot of this comes from the fact that we are only tracking states that are visible to the kernel. So states that the driver and the device are both aware about, and they used to serialize themselves, we don't know. And so this is sort of the false positives that we get in here. But we think that, well, at least with this, we're able to get a good balance between techniques that are like completely agnostic of synchronization protocol and those that try to understand synchronization protocols.
Go ahead.
So when you say false positive here, you mean things that are not in fact data races?
Yes.
But it's not necessarily true that all of the data races are bugs.
Right. Okay. So yeah. So the concept of benign races is what you're talking about. Yes. Yeah. So I'll come to that so I'm not reporting the number of benign races that I have here, and I think that's a general problem for data race detection in general, right? Because
do you have a sense for how many of these are actually bugs that we care about?
Oh, these are all false positives. I haven't gone to
sorry. They're false positives, yes.
These are all false
I
positives.
have a follow-up question.
Yes.
So these are all false positives, but you have this other problem that if you try to be too precise, you're so precise that you don't report any real database either, right?
Yes.
So when you're pursuing low false positives, you also have to simultaneously make sure that you are doing something useful also.
Right, absolutely.
Did you find any real races?
Yes. That's the next slide. So we found true races in Linux drivers. And this is after pruning away all of the benign races. We actually found this were real races. So some of them were kind of interesting. So one of those races here actually never got a Linux bug report. So I mean, the way I verified this was basically, I have my driver version, and then I keep looking through the commits in Linux. And I saw one that was fixed, but there was no comments in there. And I asked hey guys, I thought there was a race here, and yeah, it was a race. But the problem there was that the race causes failures in strange ways that are just hard to reproduce, right? And so unless you're like truly analyzing on an instruction level what the driver is doing, you would actually not find this conflicting access. So yeah, for DR check, we found a total of 9 races. So we decided to like I said, Data Collider is on Windows. So we looked at each race and tried to see, will Data Collider catch this? Now, so we then model like two forms of Data Collider. One is deterministic. So one thing I didn't mention before was that Data Collider is probabilistically stalls threads. So here we're assuming that for every race here, Data Collider actually will stall the first access, right? Like deterministically. And there, we saw that it only detects just 2 of these 9 races. And the reason was because in this case, the first access was in an interrupt handler. So the example I was just talking about, the first access was in an interrupt handler. And so because Data Collider doesn't stall it, it will actually miss that race. And the other 2 then the other reason was because some of these races actually occurred far apart in time. And so while they're not, might not lead to data corruption, but they're near misses that we would like to know about. So to sort of then, so for the interrupt handling, we decided, okay, let's invert it, right? So for a scenario where the first access is an interrupt handler, why don't we reverse it such that the first access is no longer an interrupt handler, so that Data Collider could actually stall that? And we see that if we did that, and this is what I call ideal, we then Data Collider catches 6 out of the 9, right? And so the remaining 3 are basically the ones where either the 2 accesses are both in interrupt handlers or they are far apart in time. And so by checking more of the driver execution, in particular the interrupt context, we're actually able to find more races.
If you have a race between 2 interrupt handlers, aren't they serialized anyway by the interrupt delivery mechanism from the device?
Right. So let's.
How's that a race?
Right. Actually, you're right. So yeah, you're right. So the actually no, that's not necessarily true. So it depends. On a particular core, the interrupt handler is
2 interrupts in the same driver on different cores.
On different cores, right? So yeah, 2 types of right.
But even on the same core, the 2 interrupts have different priorities or outcomes,
well, in
right?
in Linux, it's not. Yeah, it's not in Linux. Yeah, not in Linux. Yeah. So it's really the separate cores. Okay, so yeah, and so this is the sort of the balance you were getting to, right? Which is, you could either try to be more precise and detect nothing, or try to be too precise and get too many false positives. And so we sort of think that we're sort of somewhere in the middle, but there's definitely room for improvements, at least in terms of the false positives. All right, let's see, not doing a long time. DMA, so DMA check actually detects DMA buffers, bugs in DMA and how drivers use DMA buffers. So a DMA buffer is basically some part of a system memory that's shared by the driver and the device, such that the device can directly copy data off it, which is good for I/O performance. So a number of issues come up with how DMA buffers are used. One is the fact that they're shared. So we have to avoid the driver and the device racing on it, and which I don't know if that gets to your question. So the driver should avoid racing on the buffer while the device is using it. Now, the other issue that comes up is the fact that the driver and the device actually access the DMA buffer through different paths, right? So the driver goes through a cache, the DMA buffer uses physical addresses directly, and so this leads to all sorts of coherence issues, and so you have to sort of be careful in terms of how you create your DMA buffers. In particular, you should ensure that your DMA buffers are cache aligned. Finally, DMA buffers are system resources. The driver should avoid leaking them or mapping them in inconsistent ways. And so all of these rules because Guardrail gives us an instruction trace of what the driver is doing, we can actually write checking tools to check for violations of these rules. And in fact, I did that for Linux drivers, and I found about 25 violations of this nature, 7 of which were racist between the driver and the device. And there were about 4 cases where the DMA buffer was misaligned. Now, what's interesting is that previously no one's really studied this kind of violations before, but the fact that we have an instruction trace allows us to arbitrarily check for different rules. And in fact, the way I went about this was I picked up the Linux documentation about how to write DMA. And I'm like, okay, these are the rules. I can write this up as a check-in rule. I have an instruction trace of the driver. I am going to, I can find these violations. So.
Do you know how long they've been in the base before we detected them?
Well, okay. I don't know exactly how long it's been in the base. So my Linux kernel that I use for my evaluation is quite old, actually. And so some of those devices might look really old. But the other thing that I found out, because I contacted the DMA expert on Linux, is that not all of these bugs actually will cause like an actual crash or a corruption. And so people have been reluctant in actually fixing them. But it just, I mean, this tool just actually shows like a new breadth of correctness checking that we can apply on drivers, which is one of the reasons why I went down this direction.
How can you know if it's a race without knowing the details of the hardware specification? Because the way the Julep driver works is you write some stuff and then you set a bit, and that bit says, I'm done with this, it belongs to the device now. So it's perfectly safe to modify this until that bit is
So
set.
when you're saying race here, this is a race between the hardware and the software?
Yes.
Yeah.
Wow. So the answer to that, I mean, to be precise, you're right. So like, but what I've taken here is really what the Linux kernel developers recommend in terms of how you use DMA. So there's an API for mapping a DMA buffer to a device. And the idea is while that is done, then you should not touch. The driver should not touch that piece of memory. And so what I am doing is basically I'm looking for those maps when they happen. And at that point in time, you're right. You know, maybe the device hasn't started using it. So it's somewhat more conservative than reality. But it's just like this is the encoding that, I mean, this is at least what the Linux documentation requires. Now, if I had the device logic, I could also encode that and say, well, until the driver writes to this particular control register, the device hasn't started doing DMA. Right? But you actually get to a point of one of the limitations of this work, which is that we can't directly, the analysis cannot directly examine the device states. We're sort of relying on the driver to do this, like to poke the device register to read. So that's sort of get into that. But this was just an interesting direction to go in, especially since issues like this don't exist in the user level. Unlike the data race exists in user level, memory check, memory faults exist in user level. So.
When you reported these bugs, what was the uptake in the developer community?
They were like, it's not, they don't cause any crashes. And like I said, this is very old kernel. So they were not particularly interested. So that's basically the bug detection effectiveness we get by doing Lifeguard style instruction grain checking on drivers. So I built this, so this is my design. So now I'll talk about the end-to-end performance, but first let me just show how I built this. So for my design, I basically built my prototype where the analysis runs in a separate virtual machine from the driver. And so it's isolated in that sense. This is done in Linux, as I said. I used Zen to build my interposition layer. And in particular, and also, so that's sort of how this picture looks. And then for my instruction tracing, I sort of rely on the LBA hardware-assisted instruction tracing. And so this essentially is what the current prototype looks like. All right. And this is all in simulation because hardware tracing doesn't exist today. And in particular, I just sort of want to point out, like, I mean, this is sort of like your conventional system setup. But I reserve about 0.5 megabytes of memory for holding the instruction trace. And in my simulation, which is this is actually in Symix, I evaluate like protecting the network card and a hard drive. And the driver VM has 2 virtual CPUs. The analysis VM has 1. This is a dual core system that I'm simulating. And so, and in particular, I'm measuring end-to-end performance. And in particular, I'm looking at what will it cost to protect my device from any of this kind of errors in an online fashion. And these are the 2 drivers that I use. These are Linux. These are stock Linux drivers, right? So real Linux drivers. So this is what the end-to-end performance looks like. So here I'm reporting the performance normalized to Linux. Right? And this is for the disk workload using the postmark benchmark, which tests different kind of file operations. And here I'm reporting the transaction rate, the read rates, and the write rates. And here, we see, the performance is not so bad in some cases. I mean, in a lot of cases, we have less than 10% impact, although there is like 1 or 2 where we have like 12 to 13%. Fortunately, this is not quantified here. I have some backup slides that I can get into that. Yeah. What about network? So here for network server, I'm normalizing to throughput that a server will deliver, normalized to Linux. Same, Linux is 1, and I use a range of network applications. And in general, the performance seems good, reasonable for most of these benchmarks until we get to network streaming, where I'm losing close to 60% performance in the case. And then the question is, why is network streaming so bad? Well, it's because this just reflects the frequency in which the driver performs I/O operations. So the frequency of, and this are in particular, I'm reporting here the device register accesses, which is how I/O operations are performed, and I'm reporting in particular the reads and the writes. And so one interesting observation is that well, there are usually more writes than reads, especially in the network space. I mean, this is kind of interesting, and this scale is on the log scale, so each is an order of magnitude difference. And we can see here that the stream benchmarks are actually performing an order of magnitude more device writes than other benchmarks, or at least. So while this sort of shows like the worst case, because what happens there is this is the point where the Lifeguard has to catch up. We have to stall, the Lifeguard has to catch up. And so even though this shows like the worst case here, but the good thing is that this doesn't seem to be prevalent for a lot of workloads. Okay, all right. So sort of that's the end of Guardrail. And so just to quickly go through some of the future work that I intend to do. I intend to continue in this direction of looking at device driver reliability. And in particular, the first thing that I would like to do is see if I can actually protect the operating system kernel as well. But this is going to be quite challenging relative to the interposition layer that I had here, because the kernel driver crossing happens much more frequently than the I/O driver crossing. So this is going to be really tricky. And so maybe speculation might be a good way to go rather than stalling the operations, and so assume that the operation is successful and sort of unwind it if it turns out to be unsafe. And then the other challenge here is that the granularity with which kernel and driver share memory can be at a sub-page level, right? Because in the same address space. Whereas for the device, everything's on a nice page granularity, right? And so this makes it, which makes it easier to restrict access. But now when you want to restrict access to sub parts of a page is going to be really hard. And so I might be looking into things like maybe adapting the memory allocation policies in the kernel so that driver data goes into separate pages from the kernel. And of course, I also want to tackle the virtualization overheads that I'm seeing here with the interposition layer, where I would like to have something like a lightweight virtualization now, and then asynchronous I/O writes. Now, this one's kind of interesting. So I showed that the device register writes were really the big, killer, performance killer, and this is because in the virtualized space, the I/O writes become synchronized. It becomes synchronized, which is bad, especially if your your driver does a lot of those. In fact, while the I/O reads are get worse, like maybe 5x slowdown, the I/O writes are actually like 30 to 40x slowdown, and simply because in the non-virtualized space, I/O writes have been made asynchronous anyway. Right, so the fact that you issue a write to a device doesn't mean you get a response back, but your thread can continue executing. But with virtualization, everything just sort of becomes synchronous. So I would love to explore the ability to do asynchronous writes where the guest continues executing while the virtualization layer takes on the responsibility of actually completing the I/O writes for it. And so with that, my contributions, basically I've looked into decoupling as an idea for improving the performance of Lifeguards. And I've shown that we can actually contain bugs even though we're delaying the detection of bugs. And this is great because then we can use increasing processor counts to actually improve runtime monitoring in general. I've proposed novel software optimization for existing Lifeguards. So these are existing Lifeguards that I did not write myself, and I was able to get good speed ups for them by basically parallelizing them or applying compiler optimizations. And then I've sort of gone into the kernel space and said, say, okay, what if we could do this sort of detailed correctness checking in the kernel space? And I've shown this is practical using by decoupling. Here I've shown a framework called Guardrail, which actually safeguards IO state from device bugs, and it does containment using commodity virtualization. I have created 3 novel lifeguards for finding data races, memory faults, and DMA bugs in drivers. And with that, I'll conclude and take questions.
I think rather than questions, we should thank the speaker because he's had plenty of questions.